Yeah. A very good afternoon, all participants, and a hearty welcome, Dr. Soldani, to this virtual platform hosted by National Institute of Technology, Rourkela. Dr. David Soldani is currently CTOY in Australia and also adjunct professor at New South Wales, Australia. David Soldani received a Master of Science degree in Engineering with full marks and magna cum laude approbatur from the University of Florence, Italy in 1994 and a Doctor of Science in a degree in technology with distinction from Helsinki University of Technology, Finland in 2006. In 2014, 2016 and 2018, he was appointed as visiting professor industry professor and adjunct professor at University of Surrey, UK, University of Technology, Sydney, UTS, Australia, and University of New South Wales, respectively. Dr. David Soldani is currently at Huawei Technologies, serving as Chief Technology and Cyber Security Office CTSO in Australia, Huawei, ICT security expert within the Asia Pacific region and chairman of IMDA 5G Task Force in Singapore. Prior to that, he was head of 5G technology E2E Global at Nokia and head of Central Research Institute CRI and VP Strategic Research and Innovation in Europe at Huawei European Research Center ERC. So, dear friends, we are highly fortunate today to have Dr. David Soldani as our guest speaker. So he will be delivering his lecture on an upcoming research and application topic, that is Introduction to AI, Artificial Intelligence for 5G Systems. It's really a great opportunity to listen to him. I thank Dr. Soldani for accepting our invitation in spite of his very busy schedule. Thank you, sir. Now I hand over to Dr. Soldani for delivering his address. Thank you.
Thank you so much for having me today, and just to check with you whether my voice is clear and slides are also visible on your screen.
Yes, sir. Yes, Dr. Soldani, it's visible.
So
voice is clear.
We can start then.
Yeah.
So I prepared this presentation that consists of mainly 3 parts. So the first is about some definitions. So we are on the same page about what AI is and the corresponding enabling technology. Then I will review the work ongoing in the standards, and I will conclude the presentation with some specific examples, use cases, and a recommendation of on future research directions. And so thank you so much for the kind and comprehensive introduction. So my experience and knowledge is especially at 2 organizations, so Nokia and Huawei, but I've been always active as an academic, and I'm still doing so. And my knowledge, it is especially on end-to-end mobile communication systems, but also I had an opportunity to look into the details of cloud computing, artificial intelligence, specific applications, the Internet of Things, and I would say also virtualization in general. Now, I would like to start with some definition which I have taken from the European Commission. and which is rather clear what artificial intelligence is, especially what artificial intelligence systems are. And this representation also allows us to understand the different concepts. So what we talk about intelligent systems, what we mean in practice is it could be software, or it could be also hardware that once are given certain objectives, they act on our behalf, I would say, and they perform some tasks, either in the physical world, but also in the intangible dimension, digital dimension. It could be like a software service, for example, by making measurements, so extracting, acquiring knowledge, data, and finally, out of this data, they decide and take the best action, usually, normally, say, following specific policies we have set a priori, and the action to take is exactly to achieve the specific goal we have given to those particular machines. And there are a number of applications or realization of artificial intelligence. We do have robotics, we have reasoning, and today I think the main focus is around machine learning, and I will give some example of deep learning application, but also some insight into the reinforcement learning. As we speak, I think that the machine learning, the technology are overall rather mature, and currently the research direction, especially on the reasoning system, because what we would like to do is not only offer, say, an AI marketplace, I'll show you through this presentation, but what the target is to sell knowledge as a service. Therefore, knowledge as a service means we need to have access to reasoning systems that go well beyond pattern recognition or action taken by agents to intervene in a certain type of environment. So now looking at the machine learning, we have different categories of technologies. So we are talking about supervised learning, unsupervised learning, and reinforcement learning. And here you have example of techniques and the algorithm to achieve this particular goal. We may start from the supervised learning, which output usually two type of results. We are thinking of classifications, or we may think of regression. Very typical is this application. I will show you also for the mobile communication system, where we use this technology for predicting, so for showing us the path, the trends, and then would allow us to draw particular conclusions. And the technology I am talking about are artificial neural networks, which consist of a number of perceptron or neuron that they are embedded, so we have multiple layers. But practically what it means here is that we have a number of parameters that can be tuned, and those parameters then are, once the model is tuned, adjusted to specific inputs to the target we have set, can be then used as an inference algorithm, which inference means to extract, derive much more rich information for a unique set of parameters that are given at the input. In addition to this, we have, for example, when we think of unsupervised learning, we have clustering and unsupervised learning. I've used, for example, in the past, when we have a number of key performance indicator and we have a little understanding how to put together this type of measurement, so we can think of an unsupervised learning technology to help us cluster, put together, characterize certain type of data, and then act on those particular results. And beyond this, an evolution of the artificial neural network are the recurrent neural network, which we provide example of a feedback loop, especially taking into consideration the history of early outputs or history of parameter settings, and technology to help us make much more sophisticated decision, and that is basically what comes with reinforcement learning. Here you have an series on I would say an intelligent agent that takes certain actions on a particular environment, which is observed, interpreted, and then based on its state and reward function, this agent can further learn so that they can improve its policy, which maps its inputs into a particular action to take on that environment in order to maximize this particular function we can define depending on the problem we would like to resolve. I would say it's not an easy task. It requires a lot of effort, especially to train the neural network. They are usually used to steer the decision of this particular agent, as I will show you later during this presentation. Now, that basically is very high-level introductions of technology, techniques, and some definition. I mean, there's plenty of literature, plenty of courses. As I said, all those technology are mature and well understood, and the question is, and the talent now is needed in order to properly and efficiently and effectively apply those technology. And in this case, we're talking about application to mobile communication system, or anyway, networks in general. And let's have a look now at the standards. So there are many initiatives ongoing, and started, I think, from 2000, so 3 years back, or 2 to 3 years back. And the first I'd like to share with you is an initiative still ongoing within the ETSI, so that it is the standardization body in Europe. And the work done by ETSI initially has been around the virtual network function and its virtualization. So you may see here the high-level architecture, they have output, and the different function we have at the different layers. So from the virtualized infrastructure layer up to the virtual network machines, and then the orchestration layer on top. Now, what the new group since 2018 has done is to introduce supporting architecture, and this initiative denoted as sorry, there is a typo here. So it is an experimental networked intelligence. And the NE group, what they've done here is to create an architecture on top that provides services, as illustrated on this slide, to the network function orchestrator. So the network function orchestrator has been already specified. So what we're doing now is simply to observe the state of the different layers here, the virtualization layer, inputs from the virtualized infrastructure manager, as well as the status of the virtual network function, and what the orchestrator currently sees or oversee across the whole network to make some decision, and then therefore support the orchestration function in terms of the way he has to reinstantiate the different functions across the network. A typical application could be, if you look at the 5G, will be on the instantiation or reshuffling of the way slice provision across the end-to-end mobile system. So the work is still ongoing. There is a number of use cases studied, but I think the high-level architecture is available, and you may find in the ETSI website. And what we need to remember here is this initiative is really to assist the ETSI MANO, so the management and orchestrator, to make proper decisions. Now, if you look at another important initiative within the ITU and the corresponding standards they have created, so since 2018, they have set up a focus group on machine learning for future networks, and that included the 5G. So this work was really to define an overall architecture end-to-end, and to provide requirements, so to liaison with the 3GPP and the corresponding organization in the hope those requirements, this architecture, this new functionality are then adopted by the corresponding standardization body. In this particular case, the 3GPP, which is not a standardization body, they are writing technical specification for them being transposed by the corresponding standardization body, which include ITU, ETSI, or like IMDA in Singapore. So what I define here, very, very, very nice, interesting work, I would say. They have introduced the concept of machine learning pipeline. And here on this slide, you do have a representation of a high-level architecture of a mobile communication system. In particular, it is a 5G system. And here we may see the user equipment is here, so the terminal is here, on top of which we may see the radio access network, which consists of base stations. So the GNB is a base station, and the different type of way of implementing it, including the studio split and the ORAN, for example, is within this category. And then on top of it, we have the core network, and then adjacent to that, we have the network management system, so the NMS, in its various, say, configurations. And connected to the core network here, we have the multi-access edge computing platform. So the target here is to define a pipeline, which means a number of functions to be chained together to perform certain tasks. So to introduce an intelligent action, or say an inference algorithm to improve certain characteristic or performance of the network. So what I define here is a pipeline which consists of a number of nodes. So to introduce a source node, you see here in this case is just embedded into the mobile phone, which is source because it's where data or performance indicator or KPIs are extracted. Then we have a collector where those data are collected, and they could come from a number of sources. Following the collector, we have a preprocessor. It is necessary to pre-process the data. You need to sanitize the data. Data are biased, so there are many things to be done, like cleaning or aggregating them before this data is passed to the model. The model is, in this particular case, as you see on the slide here, represented by this arrow, may consist of the model, or you may think of embedding the model, the pre-processing function, as well as the policy function together. But in this case, this representation is of the inference algorithm, because the model itself has to be trained on a sandbox. So that's normally done like this. You can't train the model on a live commercial network, so under production, the production environment. That's not possible. So usually, and all models are trained on, we say require sandbox, means something, simulation environment or a test environment before the real model is pushed into the corresponding recipient. And before doing that, you need to have a policy or some control mechanisms, like shown in here, that it is responsible to verify the potential impact you may have on a live network. And this is necessary, because if the algorithm does perform well, you cannot provision into the infrastructure. And then we have a distributor, which it is responsible for distributing the corresponding model or actions, depending how the system is implemented, and the sync where that particular action is taken. So in this case, you can see that this sophisticated machine learning pipeline delivers, pushes actions towards the mobile edge computing platform. And you may think of that particular use case. One way could be like, say, you are not happy with the latency you have in the system, and therefore you may think of doing something within the multi-access computing server to improve the particular performance. In addition to this, interestingly, they introduce a machine learning function orchestrator. So they pretty much, let's see, go back, copy the idea of MANO, ETSI MANO, and they think of a similar function to have in place to manage, orchestrate. So we're talking about placement and chaining of the different machine learning function. And practically will mean that this orchestrator will solve the problem of embedding these particular nodes across the infrastructure. And the MLFO comes in closed loop. So similar to the MANO here, performs actions, but also receive measurements from different parts of the network, so that that particular machine learning pipeline can be continuously optimized in order to meet your intent. Intent is nothing else, a set of policy rules that define your use case. Now, where are we today? So this work is great, but introduces many challenges. So if you think of this architecture, how the system works today, what they're introducing here is an additional layer. So today's system, they are represented by three layers of protocols. Say you do have the user plane, you have the control plane, you have the management plane, and now we will introduce this artificial intelligent plane. And we need to think of how the two systems will interact, work together in a compatible manner. And if you could think back here, this is exactly what the NE is trying to do, is to create something that will interact with the management and orchestration function. Now, let us have a look at what 3GPP has done. So 3GPP received requirements from ITU license statements, and they need to think of how to bring those new concept, architecture, functions, interfaces into the existing system, which is the 5G mobile communication system, already finalized in the release 16. We are now discussing what's going to be next in release 17 and 18. Now, if you look at the release 16, the 2GPP has already incorporated requirements into one technical report and two technical specifications. So the technical report here discusses the use cases, so that this new function they have introduced, denoted as network data analytics function, which is a function of the core network. Therefore, the work you find in the internet, like I found this, are incorrect. So, but probably they will enhance it so that a function of the core may also be thought about as a distributed function, including function that would apply to the edge, namely the radio access network. So we are not there yet. That's what I'm presenting now. I'll show you one of the papers I've accepted on one of my special issue on artificial intelligence, which is very interesting work. But at the moment, what we have in 2GPP is simply the definition of a network data analytics function, which applies to the core network, so exchange services with functions. You have here a number of them, including application functions, the ODM you have in the core network, and accordingly extract, collect, it's a sort of collector relevant data to meet then a number of use cases. So here you have 9 use cases, which I have aggregated in terms of load level computations and predictions, load analytics, congestion information, and then how the network performs when in the case of heavy load. But they're also thinking of using these functions for improving the end user experience. So we are thinking of service experience, UE expected behavior, the terminal mobility, UE communication pattern prediction, and of course application to a quality service, which with the 5G, the quality service is defined really at the granular level in terms of flow components. So if this function can communicate with the PCF, so the policy control functions, we can really perform actions at the single packet level. And now I would like to present a work which we have accepted for publication coming now in the IEEE Communication Magazine, November. So that means this month, by some colleagues working on a European project. So the work is entitled Artificial Intelligence-Based Autonomous Control Management and Orchestration. That's the title. And here you have the author. So it's a very interesting work, and we accepted this contribution for many reasons. For its original contribution, but I think it is correct. It's one work that tends to bring together the different contributions I presented to you earlier, and in addition to this, what they are also doing is they propose how basically a neural network could be then insert into this overall framework to improve the performance of the system, really end-to-end across the user plane, control plane, but also the management. So let's have a look at now how this system works, and let's start observing this high-level architecture. So the high-level architecture consists of 2 planes. Of course, the actions are then affecting the user plane, because that's what we want to improve here. Yeah, in addition to optimize the configuration of the control and the management plane. So what I have done here is they have analyzed the management and orchestration domain and the control plane. So these 2 distinct domains. Now, and here you have the different models they are using and the origin of where this particular function is defined. So we have 3GPP models, as I presented you earlier. And for the 3GPP, they have taken two main functions. The one I have presented on the earlier slide, so the network data analytics function, which is here. And the network data analytic function, as I said, collects data low level at very granular level. And so we are thinking of specific network function, as well as we can extract indicators of performance of a single network slice instance. Okay, that's basically here. And in this case, the output of this function are then used as an input of the AI functions they have defined, the algorithm they have defined. And those algorithms they have defined, they operate in short term, mid-term, and long term, depending on the tasks they have to perform. So in this particular case, we have an artificial intelligence short-term forecast function that provides then services to the PCF, and the PCF, the policy control function, will then enforce that particular decision based on the prediction of the function those authors propose. So similarly, they have defined function for the management and orchestration domain. And in this case, they receive service from another function defined in 3GPP, which is called management data analytics function. It has been there already. It's not coming with the artificial intelligence. It is a function that has to be there, because that's the function that collects low level at both network function and network slices level. So it's already well defined in 3GPP. So this collected data are then passed to the AI long-term forecast function, basically a network like here, and those particular prediction and then injected to the network function visualization orchestrator engine, which I've shown you earlier, coming from ETSI, and therefore the optimal or improved placement of a particular network function can be achieved. Or we may think of using this load history as an input to the IMTF to achieve midterm a forecast and provide this input to the virtual network function management engine, still within the ETSI model, so that we can achieve a resource scaling decision. So basically, resource scaling decision means that I can provide more resources to that particular function to perform better. I don't know whether if you have played with the cloud computing. So I'm thinking of the public cloud with Azure, or you may think of even the Huawei public cloud. You have that as a parameter that you can scale out this resource. So in this case, what they're doing is exactly to use this kind of function so that the performance can be improved, or if you have an excess of computation, this system can be scaled down. And then, so that's basically what concerns the management orchestration layer, as well as the control layer to perform tasks within the core network. And what remains here is the radio access network. As I said, as of today, 3GPP has not done that. So what I've used here, it is work coming from ORAN. So I hope you are familiar with this initiative. It is practically speaking, it's nothing new. What we are doing here is to open up more interfaces between the control plane and the user plane as well as the management plane or the radio access network. And what they're doing here in practice is to insert their function between two other functions defined by the ORAN denoted as RNIB, which stands for RAN intelligence, RAN network information base, which is simply collecting information. In this case, they are considering load information of different flows. As I said, the quality of service ended at the flow level in 5G, or they could be flow aggregates when we think of the bearer itself. And out of this information, they are using their inference function for short-term forecast, because here we are well below 10 milliseconds type of action. If we think of providing inputs to the RAN intelligent controller for the new scheduling policy updates. So that's basically the architecture they have defined, the concept they have defined, and then they have in this paper they have also run several simulations, and they have validated their results. In particular, proposing also a neural network encoder and decoder structure. So basically, this box here, it's then realized using this complex convolutional neural network. And also the idea, I like the idea here, because this is something I've done also in the past, that you can represent, yeah, that's a very good intuition, but it's not novel. I've already seen this 20 years ago on self-organizing in maps when I was in Finland. But I like this because they are considering maps of KPIs. That's what we do in practice, right? What you do here, you look at your network, and then you see popping up different type of indicators, red, green, yellow. There could be alarms, or there could be KPI, not performance, but they're really linked on a map. So they give this map as an input to the encoder. So you have the convolutional neural, to the convolutional neural networks, as you know well, and then this data are passed to other neural networks. They are fully connected here, and then the results are used as shown here to provide inputs to the corresponding. So this inference output at a different level. Inference means, again, repeat, inference is to extract from a single source of information or information with more value, or information at a layer above, and this is passed to the corresponding consumer's function at different layers, but also different network domain, so that this particular actions are taken and the performance may improve. I spent quite some time on this slide because it should be clear how all those bits and pieces, this puzzle, may be composed. This is just a proposal, but I found that really interesting, and it performs. So I've seen in this work that the performance are there in long term, short term, but also those algorithms work very fast. Okay, so that's basically is the first part. What I wanted to introduce you, and also invite you to have a closer look at what I presented, because that is the future. There is still a lot of work to be done, and all of us may contribute, academics or people from industry. Now I would like to share with you what Huawei has done. I would say since end of 2017, the launch of this architecture concept, where 2018 and today we have mature product. Product means practically chipset enablement available for the devices. For example, any Huawei smartphone has a particular chipset on artificial intelligence, like I'm using, for example, to read documents or helping me to find something I'm looking for by scanning simply an image, and or we may have application for the age or device in general, and for computing, general purpose related computing in the cloud. And the work that has been done is really comprehensive. So that's why we're talking about the full stack. And the target was to address all possible scenarios, not, I would say, specific use cases, like we may think of images. So to look at the computer vision. No, we want to have a framework and an architecture and a chipset really capable of meeting all possible requirements across all possible scenarios. And we delivered a full stack, which means in practice chipset, ascend. I will show you what I mean later. By that, by redesigning the architecture of the processor using a Da Vinci architecture, which is a three-dimensional way of computing. On top of it, we have the chip enablement platform realized by the compute architecture for neural network, which support practically any framework. So if you are used to work with TensorFlow or PyTorch, usually I think academics, they're more around, at least the people I've been working with, PyTorch, it's fine. You may run that on top, or you may think of using the Huawei MindSpore, which allows you a much more efficient way of composing your scripts and algorithm. And on top of this, we have now available in the cloud is the application enablement platform, which is Model Arts, where you can have access to the cloud platform, where you can upload your data and train your model, and then push your model down to where this inference should take place. There could be in the device, this could be at the edge, or could be within the cloud platform. And the strategy really comprehensive. And what I'm showing you now is the softcom AI, because the target of this presentation was not to cover in general how AI can be used, which can be really interesting to look at the different type of application, especially on different use cases. But I would like to show you how AI can be used to make the mobile communication system self-driving. So that's the target. And what we have achieved here is that the ascend, so the chip has been now been placed on all over the equipment, performing different type of function. And all the modeling and the tuning is then achieved using the model art, so the application enablement, and all the architecture has been put in place so that this operation of model tuning and push the model down and inference algorithm can be automated. And practically now what we have in place is an AI marketplace where this knowledge can be found. So you don't need to make the algorithm yourself, but you have access to this AI marketplace, and you may find already model suitable for your application. As we speak, many applications are available. And I will show you application on energy efficiency, performance, and resources related to the management in orchestration application, and then also to improve the customer experience. So let's have a look at what I mean now in practice. And let me show you a video, and then we go through more detailed examples.
AI era is coming. It's making everything intelligent, reshaping all industries and bringing value to every person, home, and organization. Today, Huawei leverages smart practices to concentrate its gigantic power into a small chip. Chipset is the foundation of AI that surrounds us, which needs a revolutionary computing architecture. The Cube Compute Engine is designed from scratch based on AI computing characteristics and dramatically improves efficiency. Along with the Cube Compute Engine, other processing units are working accordingly to deliver computing power for various scenarios. This is the Da Vinci architecture, dedicated for AI workloads. The optimized ISA brings programmability, which eases the implementation of new algorithms and models on chips. In order to make development and deployment on our AI processors easier, we offer full-stack AI portfolio, which includes chipsets, chipset enablement, frameworks, and application enablement. Ascend series AI chipsets and IPs are designed to cover all scenarios. This is Ascend 310, the first Da Vinci architecture-based AI processor. With 12 nanometer process, the chip delivers 16 tops at INT8 and 8 tops at floating point 16 with only 8 watts. Our full stack portfolio breaks the barriers of AI implementation and brings inclusive intelligence to all industries. Today, we lead the future with more extensive AI computing capabilities. Envision a better intelligent world. With an unrelenting focus on ICT, we are making this happen with our partners together.
Right. I hope you just get up an impression of what I was talking about, the products, and in particular how this solution, as it's been designed, can meet really all scenarios. Now, I want to just show you where we are and some examples of application and use cases. So the target, as I said, is to have a self-autonomous, possibly autonomous, self-driving mobile infrastructure. So, which means in practice, adopting, say, the concept we are having for vehicles, for autonomous car. So we have 5 levels of autonomous realization of the system. And we may think of starting from here, for example. So those levels we need to apply now, like we have done for the autonomous driving. We would like to apply the same concept. Like you may think of driving your system, your mobile communication system. So where are we today, and what we would like to achieve in terms of these different levels, from level 0, which means all manual, all tasks perform manual, to a level 5, which means fully autonomous, which in practice means that there is no human intervention. So I think this is very far into the future, and but the target is exactly to achieve this goal. And today we are here. So today, if you look at your network infrastructure, it's only partially automated, and only a few tasks really can be performed without human intervention. And I will show you some of those examples. And the target now is to use this new technology, to use this artificial intelligence as a general purpose technology, and apply that so that the system can be really become autonomous in a way with very little human intervention. I do believe there will be always the need for a human to intervene, because there could be cases where our intervention is necessary. And in this case, we need to take remote control of the system. But practically, apart from a few cases, I think that all the business processes or our telecom service providers should be, in a way or another, automated. And if you look at the business processes of our mobile carrier operators, they consist of 4 main steps, I would say. Let's put it this way. And we start from planning and design the infrastructure. Then we do the deployment. We deploy different elements, and then once the system works, we think of improving the performance, and then we may have the provisioning of new services, including, for example, migrating the system to the following generation. And our approach has been scenario-based, so scenario-oriented. And what we have done is to break the different business processes into different phases. And for each of those scenarios, we have developed different type of solutions. Like you may see here, for the planning, we have algorithm now that to assist network planning based on specific scenarios. But we have also worked especially for OEM optimization, and fault management is definitely one of the most important applications. So the message here is that the system is really complex. Practically anything you do has to be technically feasible, but more importantly, has to be business viable. So business viable means that there is a positive business case in what you have designed and what you intend to deploy. So this approach, by looking into the different scenarios across the operator business processes, it is practically a success. So, and today we have already developed a number of applications across the different scenarios. So from planning, deployment, maintenance, performance, and provision. And here you have example of algorithm already available and also deployed and in the phase of testing as well. And now just to give you some example results to get the feelings of what I'm talking about. So planning, we have developed algorithm to predict the traffic. So that's a very typical case where you may use a recurrent neural network. I've seen them, they work very, very, very nicely. So it depends on the time frame you intend to predict. It could be like an hourly type of prediction. It could be a much longer period. That's more typical. So I've been involved in this type of work where you may use past data. Say you may look back 6 months or even a year. Then you use a part of this data for, say, the first periods of this data for training your model, and then you test your model with the remaining part already available data. And then once the model works, you may think of bringing that into the practical utilization in production. Then deployment. So this is a plug and play type of solution, and it is already in place. And what is all about, we are thinking of having a way to simplify the way the parameters are set. So instead of using a single parameter itself, we can have a policy translation to parameters that reduces basically of 90% the number of parameters you need to configure. Then in addition to this, we have a self-configuration, a plug-play system, and we do also have algorithm now to avoid the intervention, because once the system is up, we have the possibility of visualizing how the service itself works. The other application, important application we have is on alarm automation. So we are after the troubleshooting here. So we have a massive number of alarms. So the first thing is that we need to do is to reduce the number of alarms. In this case, we have shown that we may shift from 30,000 down to 300 alarms. But then the point is that, okay, if I have those alarm, I need to find the root. So what I need to do here is you need to find the root alarm, so that by resolving that particular alarm, then all the system will be fixed. So even in this case, we have developed the algorithm to reduce, or we say minimize, the time needed to resolve that particular fault considerably. And then the other application is just an example. We have many examples of performance. This is around Massive MIMO. Massive MIMO is a default feature of the system. What we've done here, we have looked at the 3 key parameters. One is the azimuth, then the width of the beam that we form, and then its power. And we have managed to optimize it through observation of the ongoing traffic. And what we found out here, that performance were improved of 2 digits. And another important application, this is the example of 4G, but also very important for the 5G, it is the concept of if you don't have traffic, basically doesn't make any sense for you to consume energy. So we think of 0 bit, 0 watt. So now you may say here, we have algorithm in place that they may decide to steer the traffic. So they're commanding handovers or camping for the mobile phones to move from cells, say they are about empty, to where you already have traffic, and therefore optimize your energy consumption, and even thinking of shutting down particular sites during particular time slot of the day. Now, I would like to conclude this presentation with some consideration about the network of the future. So around 4 to 5 years from now. So what are practically the expectations, and how to achieve them? So if you discuss with the telecom service providers, basically the expectation is to have a system as I've represented on this slide, which has 4 key characteristics. So you may see that artificial intelligence is really the fundamental enabling technology to achieve this goal. So we're expecting super connectivity. And we may use artificial intelligence, to show you earlier, to improve the performance of the system. We are expecting that is an elastic system, really adaptive in terms of the services I want to offer, but also scale out depending whether I need more capacity. So you may think of network slicing, and AI can be used, as I've shown you earlier, including the architecture, to achieve this goal. It has to be a convergent and simplified system. And this is exactly the target of 5G, because with the introduction of the 5G core network, what we are having is that it is a system. So the 5G core is the first time in history that it is a system itself that allows you to connect any type of device, independent of the access you are using. It could be like 4G, a new radio system, or we think fixed wireless access, or could be even coming from fixed access, like the next generation PON or 10 gigabit PON, bringing connectivity to the home. And then intelligent synergy. So this intelligent synergy is exactly what AI will allow us to achieve, because the target ultimately will be to have a driverless communication system. How to achieve this goal? We need to start thinking about how the network could be migrated from as it is today to what we are expecting. So a very simplified infrastructure, possibly not only connecting smartphones, but thinking of being used, an infrastructure that can be used in a multi-tenant ways, so that we don't need to build many infrastructures like today. You see here, you have many different type of service provider, different infrastructure. So we need to achieve a single physical infrastructure which carries a number of virtual slices that can be offered as a service to a number of tenants and pay as you go. And here, our artificial intelligence could help us achieve the maximal level of efficiency and effectiveness. This slide basically summarizes our expectations. And I've already introduced you earlier where we are and where we target to be. So looking at the 2025 and beyond, we are no longer really expecting any improvements coming from the traditional way of handling the networks, but we are thinking of that AI across the different scenarios I presented you apply to those particular relevant carrier business processes will help us really to achieve an automatic, say, system in where our intervention is really limited. And that concludes my speech. And I want to share with you the vision of what we would like to achieve by 2025.
AI repetitive work aggregates knowledge from generation to generation, enables cross-boundary innovation. Now is the time to build an autonomous driving network, embracing the era of intelligent operations. Greater energy efficiency, lower carbon emissions, a greener planet. Better coverage, higher speeds, stronger performance. Automated operations with zero interventions. Proactive maintenance with zero interruptions. Always online with zero risks. Voice control frees up your hands. Auto translation facilitates communication across language boundaries. Sound localization delivers intelligence everywhere. Stronger computing power. Higher energy efficiency. Wider ranges of applications. Activate pervasive intelligence to build a fully connected, intelligent world.
So I want to thank you so much for having me today, and I'd like to invite you to the Global Mobile Broadband Forum, which is this week. I think you may take that opportunity to see the latest technology developments. It's a very comprehensive review of all the solutions, products, technology of mobile communication systems on November the 12th and 13th, and they will also present the latest development on autonomous driving networks, which is a part of the solution Huawei has been developing. Thank you so much.
Thank you, Dr. Soldani, for giving an interesting talk, very interesting talk indeed. And now we are all clear how artificial intelligence will make mobile communication systems self-driven, and the enabling technologies making it full autonomous system. So it's a very interesting lecture today by Dr. Soldani. I'm very much thankful to him for giving his valuable time for this forum. Thank you so much. Any questions from participants may be raised. Or you can put, okay.
Hi, Dr.
Annapurna?
David. Yes,
Yeah.
ma'am. Yeah.
Please take over.
Hi, Dr. David. Excellent as usual, sir. So, Annapurna here, sir. So, just wanted to ask few questions. As you have shown the network traffic prediction models for UI, in that condition, how you are going to tackle the interpretability and accuracy of the ML model, what you are using there, sir?
Yeah. So the trick is the trick. I mean, the practices are they follow this approach. Pretty much is done everywhere. So what you need to have, for example, you want to predict, you want to sell a service to an operator. The operator, they're very interested to understand how the traffic will change, whether they need to activate or steering the traffic using quota service or other mechanisms. And you may use AI. So the recurrent neural network, it is an approach we have used, works. And how you do that? Very simple. You need to have access to 6 to 1 year data. 6 to 1 year data. And let's say you have 6 months data available. So 6 months data available, you may split this data into 2 parts. Say the first 4 to 5 months, you use them to train your models for predicting the traffic. And then you test it with the remaining part of the data you haven't used. That will be the very last month. That's the way you're doing. Then, not finished, because you need to do that constantly, which means then you have a pipeline of data that you drag forward. So the data carry the following month will provide you again as a sliding window data. You keep training. And the training is done offline. You cannot go to the carry network. It's not possible. You do it online, and then you use that for the predictions of the future, the coming months.
Yes, sir. Sir, I got the point at least to some extent actually. So one more thing I wanted to ask, when there are a variety of data available at your end, so in those cases, as per no free lunch theorem of the ML algorithm, so have you tested with a variety of ML algorithms and got the results accordingly?
Yeah, I mean, the results I've seen are basically mostly using recurrent neural networks. They work well. So I've seen many projects. The results are fine. So recurrent neural network, it is an approach I would declare viable. In addition to this, now we may think of looking at optimization problems. So optimization problems means practically to use there are many technologies. I'm, for example, I'm very in favor of evolutionary algorithm. I've tested both evolutionary algorithm with respect to reinforcement learning algorithms. The problem with reinforcement learning is that you need to find the optimal policy and keep optimizing the policy, which carries you from the input of the agent for the agent to take an action. And in order to find that optimal policy, you need to use an artificial neural network. So like in the work I've been involved and I've seen, you have that, deep neural networks work well. And I liked, for example, very much this approach of the paper I presented, because they may think of representing the performance in the network using maps, and therefore you can use convolutional neural network, which the algorithm mature, they work well, and then embed this functionality within your reinforcement learning function, so that you may train this neural network and then the agent it is capable of making the right decision. As I said, I'm still in somehow, I doubt a little bit, because we want to push now this AI everywhere. In some cases, I've seen like genetic algorithm performing better than reinforcement learning approach. So for optimization, for pattern recognition, no doubt, the artificial neural network. But when we think of optimization problem, that you have certain performance, yes, but what should you do? How do you change the policy? What are your new actions you should take so that the performance improve? I think that evolutionary algorithms, such as the genetic algorithm, are still working very well. I've seen, for example, my son has studied a traffic light control system, which you may think of a traffic light control system is just a base station, right? So you have you have cars coming, then the base station is the traffic light control system. Then you think of how you schedule the traffic, which means how you handle your lights, right? And he found that the genetic algorithm to perform better than using artificial neural networks in terms of reinforcement learning, because the tricky part here is, yes, but how do you change the policy dynamically that will allow you to cope with a new problem that may change? And I've seen that the genetic algorithm in this case is much easier for you in also to find the optimal parameter settings for achieving the optimal, in this case was the optimal settings of the lights of the traffic light control system. So again, we need to see practically. My suggestion is that whatever you propose has to be, yes, technically feasible, but at the end of the day, it has to be business viable. So that you need to answer the question, why shouldn't I do that manually? Yeah, why should I do that manually? So the algorithm come out has to be robust, and it has to be a solution that is really business viable at the end.
Yeah, correct. Sir, what about LSTMs and transformers instead of RNN? What you're using? So, will it be?
No, I haven't spent much time on the. I mean, I'm not in academic approach here. We are after something that what we usually do in the industry. You review the state of the art, and then you may think of what is mostly appropriate for you to use, because finally you need to deliver a solution that that works, and you don't have much time for experimenting. So what I've gone through, I have already introduced.
Thank you, sir. Thank you very much. So there is another query in the chat box. You can have a look. So the query is that in 5G autonomous network and orchestration at Huawei, how do you handle the fairness bias and ethical issues while developing ML models? Please provide an insight into the recurring technical bias in existing mechanical learning functions or neutralizing datasets you propose.
Yeah, I mean, this is a very interesting question. I think we can take that offline. It could be a thesis for a student to look into the problem, because it may also vary depending the approach you are using. Hello?
Yes, sir. Sir,
Any other questions?
I think no more questions.
Yeah, I mean, my today was to not look into any specific technology component.
Yes.
As I said, the challenge today, I don't think is into the development of a particular technology component. I think, yeah, if you want to look into the new technology, then my suggestion is to start looking now into reasoning systems, because The target is the marketplace of artificial intelligence application algorithm models is going to be saturated at some point. So what we need to have the talent that they may come to me and say, look, yeah, you have this particular problem. I am recommending you this approach. You should go ahead with a recurrent neural network instead of a convolutional neural network. Yeah, like this. That's to me the talent the industry and the market is expecting. If you want to do research, my suggestion is to start looking into the reasoning system, because finally knowledge has to become a marketplace, so that I can have access and have answer to how am I developing my plans, how am I looking into this business process to bring forward. So in that sense, I think there is still a lot to do. Then if you want to work on the mobile communication system, there's still many challenges to be addressed. I'm show you the different type of scenarios, and you need to think of where you want to work. So within an organization, you want to look at the trouble. You want to stay into the area, or you are a performance related guy, or are you more a person that wants to work in a different type of area? So depending on where you position yourself, I think there are different problems to be addressed. The architecture problem are yet not solved. The functions, as you may see today, are still to be defined, and in particular, the portability of the data, how these different applications will work is still open, without saying anything about cybersecurity, because that's also an area which has to be completely addressed, not only to use artificial intelligence to analyze possible attacks or anomalies, which is mature. Huawei has product for that. I'm thinking of the problems you may have when you bring machine learning pipeline into your system that you don't want to have vulnerabilities, and you want to make sure that the system works properly, is robust, and not once you have tuned, organized it, you put it in place, and it has vulnerability and it messes up the whole system. So that's basically what I wanted to introduce today.
Thank you, sir.
Thank you. Thank you, Dr. Soldani.
Thank you.
Thank you very much. So we are ending this session now. Next session will start at 4:30.
Thank you. Bye-bye.
Thank you.